be a bit linguistic. So try to take on this concept of Zipf as a linguistic notion, and actually underline and stress a couple of things that are really very interesting phenomena in language. Basically, what we're talking about is types and tokens. And this is sometimes not well understood. Sometimes you are in a context where people will be talking about tokens all the time. And sometimes you're in a context where people will be talking about types all the time. And these two communities, the first one being, let's say, the statistical language technology people, the second one being the linguists, they will not have a clue about the overlap that, and actually the continuum of the space that they share. So the Zipfian tail is the space where tokens become types. When single things occur that are notable. In language, stuff doesn't happen randomly. There's no noise in language. Just as an overgeneralization. So rare things are intrinsically as important as frequent things. And in fact, linguists will actually argue often even stronger than that. They will say rare things are actually where all the fun is. Would you like to use the... Oh yeah, okay, yeah, right, this one. Huh? Yeah. Okay, so if you are building computational models that model something in language, whether it's morphosyntax or semantics or information extraction, it makes sense to be sensitive to tokens. By now we know that. You need to give certain things in your model more weight than others. The evaluation metric will also favor that. So you better guess the most frequent sense, or have your priors ready to readily weighted, and your probabilities tweaked and maybe smoothed also a little. So you want to count tokens. But on the other hand, it makes sense in most computational models to be sensitive to types as well. As I said, rare events are not noise. They cannot be discarded. You can, in some cases, because the evaluation method might not notice, but in many evaluations, actually, they will pop up as a source of errors, measurable error, and irritating error, also for the user, sometimes. So years ago, so Walter Dahlmans and me and the other people in Walter Dahlmans' group back in the days, so Jacob Savrel and others, we worked on a whole battery of experiments, of which the results all show that throwing away the rare things, the low frequency things, the exceptional things, was generally not good for performance. So forgetting exceptions, forgetting rare things, and forgetting the tail is harmful. And part of this talk is stressing that again. So it's basically an old conclusion, but I haven't seen it echoed that often. In fact, I will quote Mark Steedman in a short while, who's not in this. So, is there an account that is sensitive to both simultaneously? Okay, so for that, I need to go back to a hero of mine. You sometimes have these heroes, to which in one point of your life you also take a pilgrimage to. So this is Royal Skousen. He retired but is still active as a professor in linguistics at Brigham Young University in Utah. He's the chief editor of the critical edition of the Book of Mormon, by the way, but in his linguistic life, in his scientific career, he focuses on analogical modeling. He's been in really interesting places in the US at times when Chomsky linguistics came up. He was always a bit of a loner, and his theory, in my feeling, stands out as a great example of this one method that really is sensitive to types and tokens alike, analogical modeling. So he wrote a couple of books in 1985, 1986 that influenced a certain number of people, including us. So his view is really a data linguistics view, a data science for linguistics view. where he claims that really there's nothing beyond the data that you need to model to predict linguistic behavior, to make linguistic predictions, to model language data. So in order to model the data, the only thing you need to do is store it in a memory type of place. The other key ingredient is then the analogical reasoning over that. So you have the data, that is your model, and rather than some process that uses rules or explicit abstractions and maybe exception lists, because the rules never manage to capture everything, you do analogy over exemplars, and that's it. So a really simple model, and with that you can explain a whole lot of phenomena in language, and that is what a certain stream of people in linguistics and computational linguistics have been doing. And I would claim that this is actually where modern formal linguistics comes from. So the history has changed, and our perspective on that has changed since Chomsky. But before that, I think De Saussure studied with the Neogrammarians in Germany, and this is what was one of the most prominent Neogrammarians, Hermann Paul. Basically, what he says is 50% of what we do in language understanding and production is memory, and the other 50% is analogical reasoning over that memory. Okay, he uses proportional logic, which De Saussure then took as a basis for his formal theory of language analogy, the analogy principle, where if there is a similarity, if you know a certain number of mappings, and you know that that there are similarity relations between the different sides of these mappings, then the two sides of the corner, the two sides of the square stand in the same similarity relationship. So A is to B as A prime is to B prime, and you can use this dynamically to predict actually what B prime would be if you have only B, but you have seen something that is similar to B, of which you know the mapping. And really you can turn this into a multi-neighbor version, and then you end up at something that is implementable as k-nearest neighbor classification, memory-based classification, where in new case you need to go into the space of nearest neighbors, but you actually pretty soon halt at having seen one or two or three nearest neighbors, from which you induce what the outcome of the test instance is going to be. So very local estimation of what is essentially traces of types of instances that you've seen, where the instance can be a word in context, like a fragment of language, some linguistic feature vector in general. So the output of k-nearest neighbor classification is usually a distribution of classes occurring in the hyperbole, in the hyperspace where you stopped expanding around the test item. You take the winning class, or you convert the counts that you got into probabilities if that is your thing. So this is known in philosophy as selective abduction, but it's better known as k-nearest neighbor classification in computer science. In cognitive science, you would call this exemplar-based categorization, exemplar-based learning. And in memory psychology, you would call this global memory matching. But this all refers to the same case-based reasoning, local learning, lazy learning type of, the same core idea. So the significance of the single outcome, okay? This was the monolith from 2001: A Space Odyssey, still the best AI movie, I think. So Skousen always, I mean, it's not bad to bash things occasionally, yeah, just for the sake of the argument. So what Skousen is bashing is probabilities. He hates probabilities. The first question he asks, and he asks this literally, one fundamental problem is the status of the probabilities. Do they actually exist? Have you ever seen a probability? You have seen words, you've seen language input being turned into language output, but have you ever seen the probabilities? And there is this must add to 1.0 weirdness going on. So what is that? I mean, the real world doesn't add up to one. Your brain probably doesn't add up to one. So he says, take a lazy approach to statistics. Take a bottom-up approach where one is one. You know, it's not negligible. It's not an overestimation that you don't want to re-smooth it. One is one. One is important. Two also, three, whatever. But don't convert it to probabilities. Okay, so types matter. Hypotheses matter. And for example, what he points to is it's really crazy that for example, if you like Ken Church, he wrote this great paper, Empirical Estimates of Adaptation. The chance of 2 Noriegas is closer to p divided by 2 than p squared. So p is the chance of observing 1 Noriega. The chance of observing 2 Noriegas in a piece of text is actually quite high. If you see Noriega once, you're going to see him again because probably it's an article about Noriega mentioning Noriega 4 or 5 times already. So not the logical way. But accounting for this means that your system must assign temporarily higher probabilities to words in the cache, topical words, and lower to the rest. So that's weird. So your system has to add up to 0. So if certain words become more probable, all other words become less probable. Okay. Anyway. So then there's Mark Steedman. Mark Steedman was president of the ACL, and he gave a presidential address at ACL in 2007. It was a really interesting address. It was titled "On Becoming a Discipline," so that's heavy stuff. It was published a year later in Computational Linguistics. He says something remarkable. He says computational linguistics people, we laugh at linguists because they're obviously not aware of Zipf. Linguists actually, they are aware of Zipf, and they think the opposite of CL people. They think the same. We are actually oblivious to the tail, and then Mark Steedman says it is we who are at fault here, because the machine learning techniques that we rely on are actually very bad at inducing systems for which the crucial information is in rare events. Okay. Yeah, so I think largely speaking he's right, but there is a certain class of systems that is actually quite sensitive to it. Okay, so we know, of course, this is what Zipf was looking at, and if you go into the literature of Zipfology, let's say, Sander Lestrade is here. He's one of the people who's been reading tens of maybe 100 articles since the 50s and 60s and 70s on Zipf. Zipf discovered a certain number of regularities, which in words was like the rank number of a word is inversely proportional to the number of occurrences of that word. You can actually, so Zipf's law, if you compute it, you actually need to estimate a certain parameter. Zipf allows for one parameter to be fitted to your data, which relates to the size of your corpus. And Zipf's estimations are usually quite good. Like you see here, 1,078 occurrences of the word uitermate in written Dutch, if it only knows how big the corpus is. So it sees this corpus is this big, and then Zipf guesses that number 5,000, the 5,000th most frequent word, uitermate, occurs 1,078 times. Well, in reality, it occurs 1,014 times. Wow! But Zipf is actually quite inaccurate when it comes to the head. The first bit of the head, so you actually need to bend it a little to make it fit better. That's where Mandelbrot comes in. Just mentioning it, I don't know if there's people who are really Zipfologists like Sander in this room, who are actually, so Mandelbrot, not too long ago, passed away, the Belgian genius, who gave us all kinds of things around chaos theory and fractals. Also improved Zipf, by the way, and he added this beta, which basically allows you to curve to make this bend in the first bit of the curve. This is a great. I took this from a piece from Steve Piantadosi, great piece, where actually he argues. I must mention this nugget. That Zipf curves should never be done the way they're done usually. You should actually estimate the frequency rank of one half of the corpus and compute the normalized frequency, its frequency on another half of the corpus, because you don't want the individual dots to come from the same measurement. You want these both the x and y axis measured independently. Anyway, what Steve Piantadosi shows is that if you fit the curve of a typical corpus, any corpus will have this shape. If you straighten the line, you see that there's not a spread of things. There's actually something happening here. At some point, there's all points are below the line, and then they spread. So this is actually something that touches on the very nature of the language system. I cannot go into this in more detail, but it's an interesting observation. I also want to just mention Heaps Law. Several people, including a person in Nijmegen at some point in his PhD thesis, Frank Quatrième, connected Zips to Heaps Law. Heaps Law is a law from the information retrieval world, which just relates the number of words you have seen in the corpus and the number of unique words you will have seen by that time. So seeing a text of n words, you will have seen vn unique words. This will ever get larger, but there's a factor here that limits it. It's the beta. It's a square root, basically, or about the square root if you fit it to most data, so to the power of 0.5. And there's this k value that differs a bit between written and spoken data. But you can actually see that this is not a logarithmic y-axis, but this is a logarithmic x-axis that with every expansion of your corpus, you will always see new words. This will always happen, no matter what you do, unless you're looking at duplicate data. So the lessons of Zipf and Heaps are the more text, the more occurrences of the same word, and the more new words you will see. This is a double effect that accounts for a lot of log linear learning curves in machine translation, in context-sensitive spelling correction, in a lot of natural language processing tasks. When the data is doubled, the performance of your system increases by a certain constant factor, so a log linear relation. So just a number of things that we observed that underline this effect of forgetting exceptions is harmful. So this is all data looking at several morpho-phonological and syntactic tasks up to PP attachment, which is a sort of a hard syntactic task. No matter what we did, simple abstraction always harmed performance. So we got the best performances with a pure K&N based method, and lower performances systematically with a rule-based method. And in word sense disambiguation, we typically got better scores, but we also had to tweak our parameters and do the feature selection, which was sort of implicit in the rule-based approach. But nonetheless, in the end, we did very well on word sense disambiguation in the past. And also abstraction hurts. So if you allow the rule learner to induce rules for single examples, which is the black line at the very left hand side of this graph. So you allow the rules to be generated for single examples, which would make the rule-based system as powerful as the K&N-based system in principle. You get similar performances, but if you allow it to induce rules for a minimum of at least 10 examples, then usually what you see is drops in performance. But with K&N increasing the K nearest neighbors generally is also a cause for drop in performance, but that's another phenomenon. I'll skip this. So can you abstract over instances? Can't you at least mask or abstract over information that is obviously not so important for this task? So anything that ends in Schrift in Germany has the plural en, no matter what the exact stuff is before. So can you abstract over families? Yes, you can. So in fact, you can attain a certain amount of performance. You can keep the same performance while simple K&N drops with increasing K. You can actually compile K away by carefully abstracting your instances and attaining a reasonable compression. So it's possible to some degree without damaging performance. And you basically pre-compile the K parameter locally. So instead of waiting for so real lazy learning, waiting for test, you actually learn, you go into your space, and you actually learn that here you can go to case 5, here you can go to case 7, here you stick to case 1, and you pre-compile that. So it's a learning phase that you could do, in fact, but you don't need to, because the K&N system is, I'll skip that. So lessons learned for engineering. Forgetting exceptions is harmful. It's great that I can say this again after so many years that we did the study. It remains a very important point, I think. We take this still in our current work, continue to look at this in terms of cognitive modeling. So, and also in language acquisition. So we are, so in recent work with Joan Bresnan, I've looked at modeling language acquisition in children with k-nearest neighbor methods, because they are so careful with the data, and because children do not get thousands or millions of presentations of stimuli. They just get 6 or 7 or 10, and then they start to actually learn the concept already. So again, natural statistics playing their part here. So K&N actually does a really good job in modeling that type of language acquisition data, making really accurate predictions with very, very small amounts of data. And we're also doing work with neuroscientists on the predictive brain and which models actually correlate best with the brain predicting the next word, for example, when people are listening to a story in an fMRI scanner. Okay, so here's my cheer for the type. The long tail, long live the type. Thank you.
Okay, thank you.
Okay, thank you very much. We have some time for questions.
I'm not sure how this neighbor information works, but isn't it the case that you use the measures that you use in determining the neighbors are based on abstraction already?
Are based on what?
On linguistic abstraction or abstraction already? So then it's the same thing in a way.
Yeah, so there's an interesting discussion about representation. So representation is the one word that I sort of shoved under the mat here. Of course, you can pack abstractions in your abstract representations, and then you're just modeling a very abstract model. What we often do in modeling linguistic tasks is stick to the rawest data possible. So stick to the words. We in fact invariably do that. So if you never abstract, the only thing that phoneticists or audio psychologists complain about is that, of course, we do abstract over phonological abstractions.
But how do you determine the neighbors then? If you only look at words, what determines the neighbor?
There are various, I mean, these days in computational linguistics, people would pull out word embeddings for that. But since word embeddings are not great for the tail, you can also back off to simpler. So a word is usually not the only vector that we look at. We usually look at the string of words, a local string, maybe a half a sentence or a bunch of words. So then the word in the middle might actually not be known, but some words in the context will be known and will be actually very predictive of the word that you don't know. Yeah.
So taking that further, couldn't you argue that if you look at the embedding, the context, it's carrying a lot of the different facets of the word, or the many uses of the word, sometimes one facet, sometimes another, sometimes a different combination. If you then use that for the K&N clustering, and you sit in this hyperspace, you can say, okay, when I've got this point for my known thing, and now I'm moving in this direction, so to speak, now I'm abstracting on one facet only, and the rest I keep fairly constant. When I go in a different direction, I'm abstracting in a different way. Mm-hmm. So then you can say, okay, now analogically, I'm going to model toward my unknown usage here by starting from a known thing, and now I have to understand which facet I'm moving toward, and then I push it this way or this way. And so simple abstraction, where you abstract everything out, and simple is, as you said, is dangerous, because you're losing too much. Yeah. But if you keep a lot of the, so the art becomes, how do I know exactly what I'm allowed to throw away, what facet is, right, that's the problem, right? And so maybe embeddings work, or at least the current, if you compare the character level embeddings and word level embeddings and other ones, they begin to give you the nuancing that you can abstract different kinds of things from in different ways. Yeah. But that's a very interesting approach now.
I agree. I agree. Yeah, which should, by the way, always be contrasted with simpler approaches that were good in the past. And, yeah.
So one of the things you said is that why do all these probabilities have to add up to 1? Which is kind of a strange effect, of course. If certain phenomena are extremely frequent, I just minimalize the rest to 0, almost 0.
Yeah.
So it's pushed to 0. So, but in cognitive theories, and so in our brains, we have this phenomenon that if you see things frequently, then the signal function disappears.
Mm-hmm.
So there's inhibition of the signal. So has this ever been used in modeling probabilities?
That's a good question.
So that you actually, because what is the signal function of things that you see extremely frequently?
Good question, interesting.
Yeah, okay,
no,
I just wondering about that, especially when you are focusing on the cognitive aspects of this.
Yeah, maybe food for more discussion, I think. So what we see in the fMRI studies that we do is that people, when they listen to a story, they also bump into words that they've probably never heard, names usually, or locations, and we see their brain spike at these events also. So
to have a strong signal.
Yeah.
But if you hear again Brexit, then at some point you don't hear it anymore.
Right. Yeah. So our brain is known to be sensitive to that.
But then that should somehow also have an impact on what the kind of rules that you derive.
Yeah. Well, so I think people like Charles Yang, who was one of the last real PhD students of Noam Chomsky, he's also into natural statistics. So he also agrees that argues that children learn from such small amounts of data that we can't use these simple probabilities. So there's something else going on in the brain, and because we actually have the counts. So for a lot of phenomena, you can actually go into corpora like childless or similar corpora, bigger corpora even, that show the amount of cases that the child needs to learn a word or an inflection. This is not answering your question. But
no. But that's also what I said, that the 6-year-old hasn't read as much as current machines have read or seen as data, and still, in a way, is more intelligent, smarter, or functions much better than the machines.
Yeah.
So there's something strange going on there. There's something we're blinded by the statistics somehow.
Yeah.
I think.
Right.
We don't know what other thing is there.
So I'm arguing there's another statistics that so not the probabilistic statistics.
Or this is another, just moving the discussion a little bit to another point I want to make, is the other thing is that in this is what you presented here. I mean, there's something very powerful there, and giving evidence to what language is as a phenomenon, explaining language features or properties, but one thing is not in the whole picture, and that is the world.
Mm-hmm.
And then if it comes to the world, and then also the temporal, maybe one part of the world is the temporal aspect, which probably is something which you could combine in this.
Yeah. Turn it into a diachronic.
Yeah, but then, how what is the diachronic dimension? I mean, is it what are they going to take? Is it the language of the 90s or the language of 2000, or is it the language around Brexit, around this very particular, very strong topical content that determines everything?
Yeah, no, I wouldn't do the latter.
No,
because that creates a corpus that is completely biased and skewed. So I would rather go to one person and a lifetime of reading and listening and watching subtitles and whatever. But that's of course quite ambitious, but it has become more possible relatively with the social media and the way that we store digital data.
But that choice really determines two very different. Both of them are interesting, I think.
Yeah.
But
sure.
Yeah, but I think you have to either go left or right here in this choice. Yeah.
I think so too. Yes.
Okay, so we have 2 more questions, and then there's the coffee break.
Now, I heard this argument about the 6-year-old child twice already today. Yeah. I think you're missing the point that the child is not only executing the text, but also the calculation.
Sure.
It's a very important difference.
Yeah.
It only reads text when it's about 6, 7 years old. So to start reading how to see. So it gets a lot more information than just the text.
Yeah.
That might explain his or her intent.
So how do we give the computer that information?
Not use data, only use not media data.
Yeah.
Yeah, I think you let you off the hook a little bit too easily. He's too polite. So, that's not what my wife says. I'm not going there. So I think what he was pointing out is that in your k-nearest neighbor space, there is all these dimensions really carry interesting meanings. I think that's also what your question was about. And he was encouraging you to try to understand what it means if you move around in that space.
Yeah.
And you're saying, well, you're not interested. Just k-nearest neighbor, it gives me the answers I want, and what these different dimensions mean, and if I move horizontally or vertically in the space, I don't care.
Mm-hmm.
I'm shocked by that lack of interest in what those dimensions in your space mean. So this is the less polite version of that was said.
Yes, exactly. Yeah, so I'm working with linguists to actually open these models up, and I'm showing them like these models do really interesting things. So for example, they don't. So in an MT system, which you can do fully memory-based, it's like Google Translate, except not probabilities, but it has the same performance. What does the machine translation system learn? What representations are used in making the correct memory-based, correct analogical inferences? And the answer is it's kind of a constructicon of n-grams of length 3, 4, 5, 6, and we're also working on skipgram models. That's really interesting, actually. So the distances in that space form the best, give you the best, relatively best performance. And you can also play with those dimensions and switch a possibility off, like allowing for skips in the n-grams or disallowing for skips. So actually you can play with these dimensions and ask and answer a partially linguistic hypothesis.
I think Ed was suggesting that those dimensions, they capture generalizations that you would so much like to get rid of. Am I misinterpreting you now?
No, it's exactly. I have a student working on latent relations, where you take something which Peter Turney had called latent relation analysis, and you say instead of the agent, patient, location, time, the n, either 25 or 200 case relations, let's just take a whole bunch of little patterns that we get out of language, and let's run essentially LDA on them and see how many little clusters we find, and put them in a space and say, oh, here's the agency cluster and instrumentality. It looks like instrumentality when we look for words that fit. It looks a lot like agency, where patient and theme look a lot like this, and here's location and stuff. You discover optimally is about 130 of them. 130, he comes to me, he said, what's 130? I said, never heard of this number in language, right? But if this thing suggests that there's 130 ways in which nouns tend to cluster around verbs, then that's something that we need to look at, because we take 2 verbs, one is sort of low-tail unknown one, or event name or something, we say, this one is sitting to this way, but we have 2 other ones, or one other one that sits in that same direction, with that same relationship to its little partner words, its partner nouns. We say, well, from anchor verb, we go to this word we know with its little nouns, and now here's this other little noun, we've never seen him before, or he's low frequency, but he seems to have some of the same words, so we should bend him the same way. So there was a paper by Manal and the same student and some Chris Dyer and me last year, which the prize-winning paper HLT, where we talk about bending these embedding vectors. They're much easier to work with than traditional representations into an ontology. You say, I got this thing, I build this vector, now I go and put it inside WordNet space. And then when I've got multiple senses, I can bend in this way, and I adapt this. That sort of continuous versus discrete adaptation is much easier than those embeddings, which is exactly the mechanism for doing this, what you just were saying here in the KNN cluster space.
Okay, thanks.
I think
Yeah.
there's so much more to say. So, yeah.